Can everyone hear me all right? Yes, nods. I love it when I get nods. All right. So, as was stated, cosmic collisions is the title of my talk, and it's a very fancy, cool way I went about renaming my research, which is the study of galaxy interactions, which doesn't really have the necessary kick that cosmic collisions has. I figured I'd go with that. I'm going to talk to you today about my major work, which is looking at what happens when the largest objects in the universe come crashing together. What happens when galaxies of similar sizes are in a collision course with each other and are forced to interact. But before we do that, we have to start off with basics. So we're going back to Astro 101. This is a lovely spiral disk galaxy called the Andromeda Galaxy. I'm sure you're all familiar with it. And we're going to break down the components of what a galaxy is before we get into what happens if we smash them together, right? That's the odd scenario. What's the normal scenario? So, galaxies have a central bulge. And that bulge is made of very old stars, and it often has a black hole in the center. And I'll talk a little bit about black holes later, because I know everybody loves black holes. And then galaxies have a disk. And that disk is made up of stars and gas and dust. So you're familiar with stars, we have the sun, the gas, which is just the major material of the disk, and then dust, which is sort of a weird, heavier, organic compound in the galaxy. Now I'm ready to pass Astro 101. We have our basics down. This Andromeda Galaxy is huge. It has about 1.2 trillion stars in it, and it spans about 200,000 light years across. A little quick basis on units. Light years is the distance it takes light to travel in 1 year. Pretty simple. For perspective, the distance from the Earth to the Moon is 1 light second. So you can imagine this thing is about 200,000 light years across. We're talking massive. You're never going to see the other side of it. However, not all galaxies are massive. This little thing in the corner, right there, it's also a galaxy. And so actually are most of the dots in the background of this image. So galaxies can look like this funky thing. It's the Sombrero Galaxy. Sometimes they're sort of nice and yellow and bulgy. Sometimes they're blue and diffuse. Sometimes they have these lovely cigar shapes with these streams coming out from the center. And then sometimes they just look like this, like a little group of stars that just so happen to all be friends with each other. So galaxies are extremely diverse. If we want to go forward and understand what happens if we bring them together, we have to understand the different types. The same way you might study different species of dog, where you see how dogs interact with one another. Edwin Hubble was the first person to really revolutionize how we study galaxies. This is a picture of him here. That's his cat. That's Edwin. His cat also is named Copernicus, a very famous astronomer as well, and I love astronomers who have big cats and give their cats big names. So, what Hubble did is he looked at these objects, which at the time were called extragalactic nuclei, and he broke them down into groups based on what they looked like to the naked eye. So he said, well, some of these are really spheroidal, they're really yellowish red in color, and they're really big. So he calls them ellipticals. There are these E suffixes here, nice big yellow balls. There are also more complex structures called spiral galaxies, which are like the Andromeda and the Milky Way. They're usually bluish in nature. They have a nice big disk and a smaller prominent bulge. And then they have these arms coming out of the center. You can have many spiral arms, or just 1 or 2 simple spiral arms. And based on how tight those arms are bound, you can sort of add extra classifications to your spiral galaxies. He added a subclass of spirals called spiral bars. Super simple. We're not going to get into it too deeply. It's just the spiral arm has this nice bar in the center, so we're driving that motion. And then there are regular galaxies, which I put on the other side of this diagram here, not because they fit in any sort of structure of classification, but because that was just sort of a nice spot on the PowerPoint that I could fit. Irregular galaxies don't make sense. They don't have lovely spiral structures. They're not these well-behaved spheroidal things like our ellipticals. They're weird. And Hubble really couldn't figure out how to fit them into his sequence either. So, a couple people suggested that maybe some irregulars, not all, form through interactions, where you have 2 galaxies coming close to each other, like these spirals here, and the gravitational forces between those 2 objects would just mess up their structure. You go from something nice and well-behaved to a plate you throw on the ground, all the pieces get scattered. And our thought is now that perhaps galaxies evolve along this classification scheme through merger events. So we can imagine that spiral galaxies, these really intricate, beautiful structures, over time will interact with other galaxies, and through that process they'll simplify and become elliptical galaxies, where most of the star formation has died down and you have just a uniform ball of stars rotating a center. Edwin Hubble is also famously known for discovering that galaxies existed beyond the Milky Way, which might seem kind of doy obvious to us now because we live in this lovely world where galaxies are a thing. But before, they were just called nebulae, like you might see the Cat's Eye Nebulae, for example. And they were considered to be in the radius of the Milky Way. But what Hubble did is he used a really great method called Cepheid variables to determine they were much farther away from us than we initially thought. And I always have to go on a tangent here, and I apologize in advance. It's because I care a lot about a group of women called the Harvard computers. They weren't actual robots. Computer just meant someone who did mathematical work for a large set of data. What the Harvard computers did was that they looked at stars on massive glass plates, which are sort of like the pictures of the day. And they measured the magnitudes of those stars by hand. So crazy, slow, simple work. But they were brilliant physicists. I'll tell you why I said that. This woman here, Henrietta Swan Leavitt, was the first to look at these stars and come up with a method to measure distance from star brightness. So she saw these objects called Cepheid variables, which are kind of standard candles. I have a nice little reminder here for you. And to keep things simple, all that means is that we understand the physics of that star well enough that we understand how bright it must be and how that brightness will change. So if we see any variation in that, it must be due to distance. So looking at all these Cepheid variable stars, she determined the distance to very far objects in the Milky Way. And Hubble just took that method and applied it to galaxies. He saw these objects in distant galaxies and determined, hey, these things are way farther out than the actual radius of the Milky Way. We must be looking at extragalactic nebulae. And thus, there are things beyond our Milky Way galaxy, and now we've returned back to the modern state of knowledge. And they named them Milky Dudes. Guys. I say that because I think the name galaxy is so funny. It just means Milky One, named after our Milky Way. So the Milky Way galaxy is just the Milky Way Milky One. Astronomers have never been good at names, you can promise me that. The closest Milky Dude to us is the Andromeda galaxy, this lovely thing I've shown you before, and sort of a little bit the major point of my talk because it's coming towards us, actually. Andromeda is special, so we know it's beyond the radius of our galaxy, but we also see this blue shift of its light. And that comes from something called the Doppler effect. So, you've all experienced the Doppler effect, I'm sure. You're standing outside, you hear an ambulance coming towards you, and as it passes, the sound of the ambulance changes, right? You hear a sort of meow. I have to do that whenever you talk about the Doppler effect. It's a rule we made. What's happening there is that as the car is moving, the sound in the front is being compressed. And so you're getting a higher frequency as the car moves towards you. And as it moves away, it's stretched out. And so the frequency goes down and you hear a lower sound. Light and sound are really similar. In a way, you could spend a whole different other hour talk going on and explaining. We're going to skip that, and you're going to take my word for it that light is like sound. It has a wave, and therefore can also be stretched, like the sound from a siren can. So, if we had a spaceship coming towards Earth on a collision course, the light we'd see would be bluer than it truly is. And if we're moving away, the light would be redder. So, by looking at the light from the Andromeda galaxy, we see very particular things called emission lines, which are just sort of indicators for astronomers, shifted towards the blue. So that means it's moving towards us. All right, I've given you two great reasons to care about galaxy collisions, that galaxies evolve through these interactions, and that we are on a collision course currently with the Andromeda galaxy. So now you should all think that galaxy mergers are the most important thing in astronomy ever. All other stuff is boring, right? Oh, it's okay. Anyway, how long do we have until this interaction occurs? The Andromeda galaxy is moving at about 390 kilometers per hour, which seems relatively fast, until you consider that the Andromeda galaxy is 2.5 million light years away. So that's over 1,000,000 billion kilometers. We're still doing tests to try and understand how long it's going to take, but the most recent estimation from Gaia puts at about 4.6 billion light years. So we've got time. We've got to just figure out what's going to happen now so we can prevent the ultimate chaos of when Andromeda collides with us. All right. So, how do we understand what happens to galaxies when they interact if we can't exist on the time scale to see it, right? 4.6 billion years. I'm not living that long. None of you are living that long. If I look at this lovely galaxy here and I just wait to see what happens and they finally come together, I will die sad. So we have to find a different way to study different stages of an interaction. And to do that, we try and reconstruct the idea of a galaxy interaction through survey data. So I can collect hundreds of pictures of galaxies which are close to each other, but sort of show no sign of interaction yet. They look nice and normal and disky still. Then I can collect a bunch of images of galaxies which are disturbed, right? Something like this with this long tidal tail connecting them. No more nice disks happening. We have weird asymmetries and lots of dust lanes. And then I could also collect pictures of something I call a post-merger, a galaxy that has just finished undergoing interaction. And they're funky. They have these bright centers full of star formation, and unfortunately, I just wish we had better light on the screen. These long, sort of massive shells of stars around the galaxy, the sort of remnants of that huge collision that just occurred. You just all have to go home and Google post-mergers later and take my word for it. They're beautiful. All right, so how do we get these images? We use large spectroscopic surveys. So rather than making it the job of one astronomer to go out on a telescope and every night look at a different galaxy, we instead make it one telescope's entire job. This is the Sloan Digital Sky Survey telescope. It's about a 3.5 meter telescope. It's pretty big, it's sizable. It's in Arizona right now. And what the Sloan Digital Sky Survey telescope does is every night it looks at a different part of the sky. So I have here a lovely image of the northern and southern hemisphere. And each of these gray dots is one of the footprints of the telescope on the sky. And so every night it just shifts one way or the other, looking at a different spot. And it's trying to map all of the galaxies it can see on that portion of the sky. So we can have a huge sample of galaxies undergoing interactions from which to study the effects of those collisions. Now, doing all right on time, we have an activity, because I love to break it halfway through before you all fall asleep. What many master students, including this PhD student here, had to do is that they had to go through and identify galaxy interactions by eye. Because so far there's not a fantastic way to really quantify an interaction. You as your human self, you just sort of know. So I want to go through a couple images from the Sloan Digital Sky Survey, and you're all going to classify them. So I'm going to show you an image, and if you think it's some sort of weird galaxy interaction, I want you to give me a thumbs up. If it looks normal and regular, I want you to give me like a nah. All right. How about this one? What do we think? Oh, more. Come on, guys. Yeah, you all know. This is a normal galaxy. Nice. All right. What about this one here? A couple thumbs up? You guys are really good at this. All right. This one. How do we feel? It's a little trickier, huh? Seeing a couple thumbs up? A couple handshakes? It's an interaction. You can barely see it there, but there's that tail between the two. That means that those two nuclei have interacted. All right, what about this one? Yeah, easy, beautiful spiral, just like the Milky Way. This boy.
Whoa.
Yeah. This is a pretty one, right? Look at those two nuclei and those massive tails. You guys are doing really superb. All right, this one. A little has some shakes. All right, good, that's correct. How about this one? This is hard. This is the problem with observations, is when your resolution goes down, it gets trickier and trickier. Seeing some thumbs ups and some shakes. It's almost 50-50. It's not. It's a regular galaxy. It just has very prominent spiral arms. And then this one. Yeah, easy peasy. All right, and finally, this one's this is my hardest. You guys are pros by now, right? Oh, come on, I can see more responses. I'm watching you all. I can see all your faces. Oh, a couple shakes. Mostly, I got 2 thumbs up back there. It is a post-merger. It's just a post-merger between ellipticals. So it looks sort of nice and circular in comparison, but you can still see those weird lumpy boys. All right. Now, you're all experts at galaxy identification. Yes. Which means I'm going to send you straight to Galaxy Zoo. Because this is this great innovation that's been put out in the last couple of years to make the public go through and classify galaxy mergers. Because you don't have to be an expert like me and know exactly how galaxies work. You all did fantastically. And so, Galaxy Zoo is a website you can just go to and select their project for astronomy, and they'll give you images of galaxies like this. And you can see here, it's got that nice tail, that wobble. It's a merger. And they lead you through a series of questions to try and identify the morphology of that galaxy. So, when an astronomer like me says, I want to look at millions of galaxies' morphologies, because one person did 10 galaxies a night and a couple million people did that, they're already classified for me. It's fantastic, and it saves me months of time. So I highly recommend, just for fun tonight, go home and look at Galaxy Zoo and see if you can practice your skills you learned. All right, so these are real images that I classified, and you saw some of them now that you helped me look through today, looking at the remnants of galaxy interactions. These are all post-mergers. And what we can find by looking at remnants is the effects the collision had. So we see they all have these really extremely bright centers from a burst of star formation once the galaxy interaction has occurred. So now we have to try and make the physics to understand why that happened. So we have to do math. Because astronomers, we always come back to math, unfortunately, at the end of the day. This is a very old mathematical simulation, just sort of a, on-paper test by Toomey in 1972, looking at what would happen if you took a massive companion and shot it by a disk of a bunch of points of mass. And using the equations of gravity, he saw how these different particles interact with each other and the kinds of structures they would form as those gravitational forces went through. So you can see that as the two come together, the disk is disturbed, and you instantly form these tails. And the tails get wider and stronger as they move apart, right? You see this extension on the galaxy down here. And using just this mathematical method of a bunch of physics equations smashed together, we could replicate the structure like this. This is a sort of mathematical structure of a galaxy merger. And this is a real one, taken of NGC 4038. So our physics are right. We can predict exactly what a galaxy merger should look like based on what happens if two objects come within a close range of each other. Now, we have much cooler ways to simulate data, and that's with large n-body simulations. Same concept, but now we're making the computers do the math. And when you make computers do the math, you can do so much more math at once, and the capabilities are endless. So you can do the same thing, and you make two fake disks. This is fake. It's pretend. Remember that. That's a real image. So the point of this here is we're going to play through a simulation of a galaxy interaction and try and watch how they change and compare it to real data. So we can watch this moment where the disk is disturbed, and if we rotate it just right to fit in the azimuthal space we have, we can replicate a real merger in our galaxy. So I'm going to play this through so we can watch the exact stages as we move towards the stage of the tidal interaction, where they have those massive tails, right? That's made it really easy to identify. But this means we've passed our first paracentric passage, and now we're moving towards the stage of coalescence. So things are just going to get trickier and trickier. You have these massive tails still, but the two galaxies are coming together towards the center. Once the nuclei are officially merged into one, they'll become one galaxy, and there'll be that post-merger remnant. I think I only have one more image here. They just have to rotate it just right. Another great thing about simulations, you can turn your camera. You can't do that in the real world. You're sort of stuck with the picture you get. Lovely. There we go. Let it fade to black. And then thank NASA. All right. Now, we want to also get a little specific. So what happens to stars when galaxies interact? Because we live on a star, right? Are we going to smash into anything? Are we going to have some sort of collision with a star from the Andromeda galaxy? I'm going to play for you now a simulation of just the star matter in the disk of a galaxy. And you can see things get flung around like crazy. So the gravitational forces on stars are massive, and many can experience an effect where they come close enough to the central massive black hole that they get flung out of the galaxy. But most actually stay with that post-merger galaxy. In fact, the chances that only one star will interact with just one other star in the other galaxy is 1 in a billion. If you want two stars to interact, that's 1 in 1 quintillion. So the sun is not going to crash into any other stars. It may get flung out, but the sun will be fine. However, there's also the aspect of gas, and gas is fancy because it's collision full. It actually experiences sort of interactions with itself probabilistically. So we can use the ALMA observatory, which is a radio astronomy. So you might notice rather than a mirror here, we have these lovely disks looking at the sky. And we can try to understand how gas will change in evolution. So I'm going to show you the same simulation, same map, but now instead of stars, it's just gas, where green is warm, pink is cool, and red is hot. So you see these two nice green warm things come together, and instantly when they interact, you see that red flash. So you're seeing the heat that comes from the collisions of gas, right? But this is also leading to a condensation of gas in the center, that nice pink material. And that's where you're getting sort of that burst of central star formation as gas condenses and forms stars. So using mathematics and using multi-wave-like observations, we can break down the different components in a galaxy and how they'll be altered by these kinds of collisions. And then they return to that lovely post-merger stage. Now, the cool thing about gas, and the reason I made you do the same simulation twice, is because gas, when it goes through a merger interaction, can be funneled into the center and fuel the supermassive black hole in the center of the galaxy. So I have an example here of a nice elliptical galaxy, and you can see this jet coming out from the center. And that means that there's gas currently flowing into the black hole in the center, fueling it and feeding it, and it's releasing this massive amount of energy from the outside. This used to be one of the many ways we identified active galactic nuclei, where the active black hole is currently consuming material. But now, thanks to telescopes like the ALMA radio telescope, we can collect lovely images of the accretion disk. So that red area is the hot material around a black hole that's being fed to it and being consumed. And so it's releasing that energy as it approaches the Schwarzschild radius. We've also observed these kind of interactions with LIGO. So you'll probably all remember LIGO from the gravitational wave discovery, where we saw two black holes merge together, and that created a sort of ripple in space-time we call it gravitational wave. And the LIGO observatory could measure that ripple, and it created that lovely little sound bite of what two mergers sound like when they interact with each other. But that's sort of the last stage of that post-merger we're looking at, right? The two black holes coming together and becoming one, and often turning on because they're being fed a bunch of gas. All right, stars, gas, black hole. We've got everything. We're ready to know what happens to the Milky Way. All right, so you're going to start out with this lovely Milky Way disk visible in your night sky, and the Andromeda galaxy, ominously in the background. It's going to get real big over time as it gets closer to us and fills up the night sky. And as it gets closer, it's going to start encountering our galaxy with gravitational interactions, right? That's going to disturb the disk. And so rather than that nice, lovely Milky Way disk, we're going to have, this funky arms happening. And you can see the Andromeda nucleus there, and the arms is sort of corrected with that interaction with the Milky Way. So from our simulations, we know we've just passed that first paracentric passage, and things are all messed up. As the Andromeda comes back around, things are going to get even more disturbed. Now you're seeing sort of the dispersion of all of that gas and stars and dust. The disk has been completely torn apart. And we're also getting that inflow of gas from the Andromeda that could fuel a black hole. This disturbance will only get worse as you start to create these shells around the galaxy, and things sort of start to become uniform, and rather than a single bar, the entire sky will be filled with these bright stars and gas that are lit up by sort of fueling of brand new star growth. Then things are going to cool out. Star formation is going to chill a little bit, and we're going to start to see two elliptical galaxies form. One, let's call this one the Milky Way, and one, the Andromeda galaxy. Now we just have to wait for those two black holes to merge together into one. So if you're an alien astronomer, you might be listening out for that gravitational wave, that little blip, then we know the two black holes have come together. And then we'll just have one big elliptical galaxy in the sky. No more lovely Milky Way bar. And that's, of course, I think that means we have to rename it. It's no longer a way, no longer particularly milky. And so astronomers, in our wonderful hindsight of knowing that naming things from the past has never done anyone harm, we're going to project that we should call this new galaxy Milkomeda. That is your new home in 4.6 billion years. So write it down so all of your ancestors, all of your descendants understand that you knew it first. All right, and I will take your questions now.